Imagine a substance that pervades the cosmos, shaping the very structure of the universe while remaining invisible and undetectable. This is dark matter, one of the greatest mysteries in astrophysics. Despite being invisible, dark matter makes up about 27% of the universe's total mass energy content, compared to a mere 5% for ordinary matter. The rest? A baffling force called dark energy. But that's a story for another time. Today, we focus on dark matter, what it is, how we discovered it, and why unlocking its secrets could revolutionize our understanding of the cosmos. The story begins in the 1930s with Swiss astronomer Fritz Zwicky. Zwicky studied the Coma Cluster, a massive collection of galaxies, and noticed something peculiar. The galaxies within the cluster were moving so rapidly that their visible mass couldn't generate enough gravitational force to hold them together. By all rights, the cluster should have flown apart. Zwicky proposed the existence of an unseen missing mass that provided the necessary gravitational pull. He named this mysterious substance Dunkle Materie, or dark matter. For decades, Zwicky's idea was largely overlooked until the 1970s, when astronomer Vera Rubin observed something equally perplexing. Rubin studied the rotation curves of spiral galaxies and discovered that stars at the edges of galaxies were orbiting at nearly the same speed as stars near the center. This contradicted Newtonian physics, which predicted that outer stars should move more slowly due to weaker gravitational forces. The only explanation was the presence of an invisible halo of dark matter surrounding each galaxy, providing the extra gravitational pull to keep the stars in orbit. But what is dark matter? Unlike ordinary matter, which is made up of protons, neutrons, and electrons, dark matter doesn't interact with light, electromagnetic radiation, or any known forces except gravity. This makes it completely invisible to telescopes and incredibly difficult to study. Scientists believe dark matter is made of exotic particles yet to be discovered. One leading candidate is WIMPs, or weakly interacting massive particles. These hypothetical particles are thought to be hundreds of times heavier than protons, but interact so weakly with ordinary matter that they pass through it undetected. Another candidate is axions, ultralight particles that could explain certain quantum phenomena. A third possibility involves sterile neutrinos, a heavier and more elusive version of the neutrinos we already know. Despite its invisibility, dark matter leaves behind clues through its gravitational effects. One key piece of evidence comes from gravitational lensing. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the object's gravity bends the light, creating distorted or magnified images of the background galaxy. This bending effect often reveals far more mass than visible matter alone can account for, pointing directly to the presence of dark matter. The cosmic microwave background, the faint afterglow of the Big Bang, provides another vital clue. This ancient light, which has traveled across the universe for 13.8 billion years, carries imprints of the early cosmos. Tiny fluctuations in the CMB reveal the distribution of matter shortly after the universe began. These patterns show that dark matter played a crucial role in forming the first galaxies and clusters, acting as a cosmic scaffolding that pulled ordinary matter together through its gravitational influence. Simulations of the universe further demonstrate the importance of dark matter. Without it, the universe would look entirely different. Ordinary matter alone wouldn't have been enough to form galaxies, stars, and planets. Dark matter's gravitational pull was essential for creating the cosmic web, a vast network of interconnected galaxies and galaxy clusters that stretches across the universe. While the evidence for dark matter is overwhelming, detecting it directly remains one of the greatest challenges in science. Experiments like the Xenon 1T and LUX detectors are placed deep underground to shield them from cosmic rays and other interference. These detectors aim to capture the rare interactions between dark matter particles and ordinary matter. Meanwhile, particle accelerators like the Large Hadron Collider search for signs of dark matter in high-energy collisions. So why does dark matter matter? For one, it's the glue that holds the universe together. Without it, galaxies and galaxy clusters would fly apart, and the large-scale structure of the cosmos would collapse. Dark matter also provides a window into new physics, potentially unveiling particles, forces, or dimensions we've never imagined. Furthermore, understanding dark matter could help solve other cosmic mysteries, such as the nature of dark energy or the ultimate fate of the universe. It could also revolutionize our understanding of gravity and the fundamental laws of nature. In the grand scheme of things, dark matter is a humbling reminder of how much we have yet to learn. Despite centuries of scientific progress, we're still in the early stages of understanding the universe's true nature. As we continue to explore and experiment, the secrets of dark matter will undoubtedly reshape our understanding of reality itself. Dark matter isn't just a mystery, it's an invitation, a challenge to push the boundaries of human knowledge and unlock the secrets of the cosmos. The journey is far from over, but one thing is certain: the universe is far stranger and more wondrous than we ever imagined.